So, hi everyone. In the last few videos, we have covered a few modules of Cosmo suite, such as Cosmotherm. We have also covered basics of turbomole, doing basic calculations such as electron affinity calculation or geometry optimization and few others. So in this particular video, we are going to see COSMOquick. COSMOquick is also one of the other module of Cosmo suite. So in the last few videos, we have seen that the module such as turbomole, which is used for the quantum chemistry calculation, it basically uses the electronic structure of a molecule to generate the COSMO-RS surface from the scratch. But when we talk about something as COSMOquick, it uses the fragment-based approach. So now, before going into depth of this particular module and what all sort of calculation it can make, we have to see that what is this fragment-based approach. So this fragment-based approach, it uses databases of the pre-computed Cosmo fragments and build molecule from these known pieces. So let's try to understand this statement in a little bit of detail. So we basically break the input file into known fragments. So what is input file? Input file is basically the molecule. So that particular molecule we basically break down into certain fragments. Usually these fragments are functional group. It can be OH group, it could be ketone, it could be aldehyde or any other groups which made to form that particular molecule. Then we retrieve the pre-computed Cosmo data for each fragment. So already there is pre-computed data, Cosmo data, and we try to retrieve that for each of the fragment. We stitch them together to estimate the sigma profile. So in the Cosmotherm video, we usually calculate the sigma profile as you have seen, but that particular sigma profile or that COSMO-RS surface is generated using the quantum chemistry calculation or DFT based approach. But here we are not using that. So it makes the calculation a little bit more or much faster. And that can be used to predict properties via COSMO-RS. So let's see that what all properties we can calculate. So this is how the graphical user interface of COSMOquick looks like. We can of course draw the structure if we want, and it is same as the turbomole video as we have seen. But here I'm not going to draw any structure. We can go to the start menu also. So here we can see that what all different calculations or property calculations we can do. So starting from QSPR and ADME properties, solubility prediction, partition coefficient, co-crystal phase diagram, co-crystal and solvate screening, and many more. So let's go to the input section and try to import some data which I already have. So if I come up here, so I have some list of smiles or a list of molecules which has been provided. So let's go for paracetamol, and in this particular video we are going to go for the co-crystal screening, co-crystal and solvate screening. So let's open this one. So this is particularly the first step. We have paracetamol and all these different, whether it's toluene, whether it's chloroform, water, 1-octanol, then we have ethanol, methanol, acetic acid. All those are, we are going to see that which is the best co-former for paracetamol. So let's go to the next part. So we don't have that database, so not an issue. We will just cross it. So we will see that co-crystal and solvate screening or different sort of property prediction what we can do. Before going that, we need to understand the basic concept of the API and the co-formers. So API, here we are defining the paracetamol molecule. So we know that in a very basic sense, API which is having some sort of activity, it is going to bind to the receptor. But when we talk about different co-formers, what we are going to use, so all these different co-formers doesn't have any activity. So basically these co-formers are going to make non-covalent bond or non-bonding interactions such as hydrogen bond or pi stacking. So different sort of interaction with our API paracetamol. And then it form a co-crystal. So this co-crystal, why this co-crystal is needed? To improve certain properties. So sometimes say our drug is not having proper solubility, it might not be stable, or the dissociation rate of that particular is not appropriate. So to correct those properties, we usually make co-crystal combining our API and co-former. So here we will go for the co-crystal and solvate screening. So for the time constraint, I'm going to keep the detail low. So basically it defines the accuracy of the calculation, and we will go to next. Once we go to next, we have to define the target. Target basically means the API. So here we have defined, we have few other features which we can work on, but right now we are not going to explore that much in a detail. I'll go and run it. Sorry. Yeah. So now the process will start, and so as you can see, the process is going downside. And once the process has been completed, you will get the co-former ranking. So as you can see with the API, that is active pharmaceutical ingredient, that is paracetamol, with different co-formers what we have used. So what is the co-former ranking? If I wanted to just arrange it, so the first one is dimethyl sulfoxide, and we can see the values in kilocalorie per mole. The lower it is, the better it is. So in the last few videos, we have checked it, and we can also generate few of the graphs also to analyze the data better. But right now, we will keep this video till here, and in the next video, we will see that how we can analyze the graph part and how we can generate the graph using COSMOquick, and how we can calculate few other different properties. So thank you so much for watching this video. Please like, share and subscribe.